All right, so let's talk about the gas laws. So we had several gas laws we learned about in Honors Chem. Boyle's law is the law that says a volume of a fixed quantity of gas at constant temperature is inversely proportional to the pressure. Okay, so there is the relationship between pressure and volume. And what we know is that if I have a gas and I compress it, so I have the same number of particles moving at the same speed, they're going to make more collisions with the side of the container, and if they make more collisions, the pressure will go up. So as volume goes up, pressure goes down, or as volume goes down, pressure goes up, as we would expect. And what you need to internalize right now is that the pressure of a gas in a closed container is strictly based on the number of collisions with the side of the wall. It's not collisions with each other because there's so few gas particles compared to the surface of the wall, but it is the collisions of the gas particles with the container. Okay? So if I have more space, more wall, same number of particles moving at the same speed are going to hit less frequently. So if you were to plot pressure and volume, you get this graph right here. As pressure increases, volume decreases. If you plotted pressure, volume versus 1 over pressure, or pressure times 1 over volume, either way you get a straight line. Okay, so pressure is directly proportional to 1 over V. It is inversely proportional to V. Okay, so Charles's law is what we're talking about there is volume versus temperature. And what this says is if I increase my temperature and I keep my pressure the same, my volume is going to increase. So here I have a moving piston. I heat this up from 23 to 327, and as a result my particles are colliding more with the side of the wall, causing the volume to go up. Okay? I can also say that the temperature, I can look at pressure versus temperature. And if I increase the temperature and keep my volume constant, the pressure will go up, right? And you can see we're trying to keep the same number of particles, and we are simply making these whooshies, or these tails on this longer, to indicate that I'm moving faster. If I plot Charles's law, it gives me a straight line between temperature and volume. If I just plot volume and temperature degrees C, I get a line like this. It does not go through the y intercept of 0, 0, and that's because in order for volume and temperature to be directly proportional, I need to extend this line to where it hits the intercept, and when I do that I get this point of minus 273 degrees C, which we know as 0K, or absolute 0. And this is known as the temperature at which particles no longer move. Particles don't move. And we know particles always move, so this is a theoretical temperature. We've gotten close to it, but never actually there. So this is a point where I have no temperature, which means particles are not moving, and it is also, because it's hitting 0 here, this is 0K and 0 whatever volume units I have. It's also saying that I take up no space, and we know matter takes up space. So this is the theoretical lowest possible or below possible temperature. So if I plot volume versus temperature K, I get a line that makes the relationship directly proportional, and it goes through 0, 0. So if I double my temperature K, I double volume. Don't have that same relationship here between volume and temperature C. As I increase temperature C, I increase volume, but it's not directly proportional. You can see back on this diagram, here we are doubling, going from 300K to 600K. Here, it is directly proportional, so if I double my temperature, I also double my volume, and that's what you see happening here. Okay, but the temperature went from 23C to 327. I've got to get it in Kelvin to see whether or not I can make that assumption about doubling or tripling along with the temperature. Alright, so we're just talking about these so you can make sure that you can internalize. So Avogadro's law says that if I increase the number of particles of a gas, then the temperature, the volume of the number of particles will go up, or the pressure will go up. So if I have a, let's say I have this container here, right? Let's say there's a plunger on it, right? And I hold the pressure constant, or let's say I hold the volume constant. Don't let the cylinder move. I through some injection port, I add another set of particles, same number of particles. What's going to happen is my pressure is going to go up, right? If I'm keeping it the same volume. If I let the piston move, as I add more, and I want to keep the pressure constant, then the volume of the container is going to go up. But what I have here is if I have twice as many particles in the same amount of wall, then I have twice as many collisions. So if I double my number of particles, then I double my pressure, or I double my number of particles, I double my volume. This assumes constant volume, and this assumes constant pressure, right?